everyone that's participating. These events are being recorded and will be live on the iQuest YouTube channel. For bandwidth purposes, we would like to request participants to keep their microphones and video off until the end. If they have any questions during the presentation, please write them on chat. I will watch the chat box and will interrupt the presenter at an appropriate time and ask questions. Otherwise, please feel free to ask your questions following the speaker's presentation. Thanks so much. So today we're very lucky to have Christian Schaffner telling us about his recent work on local simultaneous state discrimination and unclonable cryptography. Christian is an associate professor at ILLC at the University of Amsterdam and a member of QSoft, which is the Dutch Research Center for Quantum Software, located at CWI. He is also the chairman of Quantum.Amsterdam, and would be wonderful for people that are meeting him, for anyone meeting him later, or otherwise to just get to know more about the quantum scene in Amsterdam from him. Okay, so with that, I will let Christian begin.
All right, thank you very much for the introduction, Lakshita. And thanks a lot for the invitation to give a talk here at your seminar over there on the other side of the big ocean. All right, so this work is, as you said, a very recent work that we just finished basically in a rush to submit to QIP 2022, which I hope many of you have done as well. And this is joint work with these three gentlemen here, Christian Mayens, who was a postdoc in my group at QSoft, but in the meanwhile actually has moved to Denmark and is now a tenure-track professor at Technical University of Denmark, and with Marius Osols and my postdoc Merdad Tamasbi, who are affiliated with the University of Amsterdam and CWI. And the first part of my talk is basically the contents of an archive paper with a link here that that we've actually updated yesterday, and the other one will appear tomorrow. So I don't know the identifier yet, but I will put the number here and also make the slides available on my website. So you can look there. So now to the content. What I hope you will learn from my talk is, first of all, I'm going to tell you a little bit about unclonable cryptography, well, what it is, and then show you our first result, which is kind of a generic cloning attack in this context, and then introduce this new problem called local simultaneous state discrimination and show you a few results about this. I just finished preparing this talk, so I have no idea how long it will take, but just as Dakshita said, just feel free to interrupt in case you have questions. So off we go. There's no unclonable cryptography without the no cloning theorem. So that's really at the heart of everything. So I quickly want to go over that. I assume most of you have seen this before. But nevertheless, it's such a fundamental statement that I want to repeat it here. And maybe some of you have seen my talks. I think Dakshita has, like the quantum for dummies. So this is kind of my symbols for qubits. Here's a qubit. And the no cloning quantum no cloning theorem says that you basically cannot clone an unknown quantum state. And this is Dolly the sheep that we do know how to clone, but the no cloning theorem says that you cannot do this copying operation. And the reason for that is actually pretty simple. It's because a copying is a nonlinear operation. And it's actually simple enough that I also want you to give a proof of this statement to you. Again, that fits on like half a slide. So it goes as follows. Assume you have a unitary operation, a quantum operation that copies. So that copies all possible states psi. So if you apply this U to psi and some fixed input state 0, say, just to have a placeholder, then what should come out is psi and a tensor copy of psi. So that's what a good cloning operation U does for all states psi. But we will see that this quickly leads to a contradiction, because if you apply it on a 0 state, well, then you should get a copy of 0, so 0 and 0. If you apply it to the 1 state on this input part here, then you get a 1 and 1. But you should also get that if you apply to a superposition of 0, 1. So what happens if you apply U to the superposition of 0 and 1? Well, on the one hand, you can use linearity. So you can apply this U to 0, 0. So that's what's happening here. And you can apply U to 1, 0. So that state over here. And notice I didn't normalize the states here because for the sake of the argument, that doesn't matter. So you apply to 0, 0, which was calculated above that 0, 0 plus 1, 1. But what should come out, in fact, is a copy of this superposition state 0 plus 1. So we should get 0 plus 1 tensor 0 plus 1, but we don't, because if you multiply this out, then you get 0, 0 plus 1, 1. That's the term we have, but there's also these cross terms here. So these two things are not equal. And therefore, this operation doesn't do its job on the superposition state. And that is the reason why we get a contradiction. So even though the U is working fine in one basis, say in the other basis, it doesn't do its job. And so linearity basically prevents us from having such a cloning operation. So that's a simple proof. Of course, it's not really quantifying how well or how well you can't do these things, but nevertheless, it gives an indication kind of what lies at the heart, that somehow the linear algebra here prevents us from cloning quantum information. So unclonable cryptography is kind of trying to exploit this principle. And as we've seen, it must be inherently quantum. So somehow the cool thing about this stuff is that these are really typical quantum phenomena. And because classical information can easily be copied, we do it all the time. So if you want to have this kind of unclonability feature, well, you kind of explicitly have to use the quantumness in there. And this was the original idea to do quantum cryptography by Stephen Wiesner back all the way in '68, when he was proposing a scheme for quantum money. You might have heard about trying to kind of put some states on a banknote, and then those can be verified. But this bill cannot easily be copied or cloned because of the quantumness. And of course, this is also at the heart of quantum key distribution, maybe the most famous applications of quantum cryptography. But then over the recent years, many other applications have come up, have been proposed, such as certified deletion, unclonable encryption, clonable decryption, copy protection, secure software leasing. And I cannot list all the citations here, so I went for one, and there's many others. And probably this list will go on. So there's still stuff to be added that will exploit this kind of phenomena. And if you want to know more about all of this, then I really recommend you to watch Anne Broadbent's tutorial talk from QCrypt 2021, which was held online. We organized it from Amsterdam, but you can see a YouTube recording, but also Anne's slides are great to kind of get an overview of this area of cryptography. So I really recommend you to go and have a look there. Because what I'm going to do is I'm going to zoom into this part here, clonable encryption, which has been proposed a while back, but then kind of picked up again by Anne and Sebastian, which I actually can see is in this talk. So great, welcome. And in order to kind of define what that is, we have to kind of set the scene, and we're going to talk about encryption schemes of classical messages. So here we have a key generation algorithm that picks some key k from a classical distribution pk. We have some classical message, say an n-bit string, and in such a quantum encryption of this classical message m, we'll just turn that message by the encryption scheme using the classical key k into a quantum state. And that you then transmit over a quantum channel to the recipient. And the recipient, she can decrypt that state by doing a measurement, by knowing the classical key, doing a particular measurement, and hopefully get back the original message. So you have the standard kind of property we want is correctness for a cryptographic scheme, so that for any key we generate in this procedure and for any message, it should hold that the probability that if you encrypt an arbitrary message, any message m, so you turn it into a quantum state and then you decrypt again with the same key. So you kind of do this measurement and you should recover the original message with probability 1. So far, pretty standard. Now, the more tricky part is defining the security notions. And here we're going to talk about a cloning attack following what's been proposed by Anne Broadbent and Sebastian All. So that works as follows. We now look at the random uniform message. So when I use these arrows here, then basically they're picked uniformly from that set, the message. And then message is sent to a cloner. So that's our pirate here. And that one carries out a cloning operation. So that's described by this quantum channel that takes register R and turns it into registers A and B, so for Alice and Bob. And then after that cloning has happened, the key is revealed to Alice and Bob. And then Alice and Bob, they try their best kind of to perform a measurement given the key to figure out what the original message M is. And hopefully, if it's no unclonable scheme, then you cannot succeed in this task very well. So not both players can recover the original message. So formally, one can define the success probability of such a cloning attack by taking a supremum over all possible attacks. Then this is an average over the messages of n bit strings. So 1 over 2 to the n sum over m. And then we also take the expected value over the keys, however they are generated. And basically take an encryption of this uniform message m, so that's the quantum state. Then we apply the cloning operation, so whatever the cloner does, and then optimize also over the kind of recovery operation, or try like the local operations that Alice and Bob do in order to figure out what this message was. So that's what Broadbent and Lohr defined as p-win uniform. And of course, a related notion and slightly more tricky. So maybe I'm going to switch back and forth between these two slides a little bit because a few things change. Is the so-called Cloning-Indistinguishability Attack. So this was one of the contributions of this article, kind of introducing this security notion. It's very similar. Just notice, for instance, here, there's a slight change. Now we have 2 possible messages only. One is the all-0 message, and then there's another message, M1. And if you've seen the cryptographic indistinguishability definitions before, then this might look pretty familiar to you. If you haven't, don't worry, I will explain it. So here we basically want to distinguish just between 2 messages, namely M0 and M1. So the sum before was over all possible messages. Now it's just over this single bit that says whether we are encrypting M0, which is just the all 0 string, or M1. And the rest is the same. Now basically the cloning operations, and then the players try to recover that bit B. And we call a scheme secure if and only if this probability to win in such a cloning indistinguishability attack, it should be pretty close to 1/2. So you can always win with 1/2, so when you have to guess a random bit, but you shouldn't be able to do much better than that. It should be, this probability should be upper bounded by 1/2 plus something negligible in the security parameter. Yeah, so far so good.
Yes, this is
Paul,
a good time.
I see a question.
Yeah. Yes, Paul has his hand raised.
Hi.
Hi.
M1 here is any arbitrary message?
Yes, M1 is actually even chosen by the attacker.
So doesn't M1 include M0 then, where everything is 0?
If you choose M0, then you will have a very hard time distinguishing between M0 and M1.
Well,
so
I'm just saying doesn't M1 include M0 as a possible message?
Yes, indeed. But that will never lead to a good attack.
I see.
So if you want to optimize your winning probability in this attack, you better choose a message that is different from the all 0 string.
So I guess the thing that I'm confused by is isn't Elmore Fudd on the left side here? He's the one who's choosing the messages, and then the attacker is the cloner.
Right. So here, yeah, that's this picture is not completely clear about that. In this case, the cloner can actually choose M1. So he will try to optimize it as much as possible in his favor, kind of make his job as easy as possible. M0 is fixed, but M1 it's up to him to choose.
I understand. Okay, great, thank you.
That's the kind of the spirit of these cryptographic indistinguishability notions. The attacker can first choose two messages, and here one of them is fixed, but that's actually, I think, equivalent to just choosing two messages and then trying to distinguish between them as well as you can. So it's kind of the worst possible, or you give most of the power to the attacker.
So just again, so I'm sure. So the attacker can decide which of the two messages, then they give them back, and then those messages are then encrypted, and then the attacker will try to clone them and see, are they able to clone, and right. After this encryption has happened, are they able to get a reliable clone that they can then identify what their original messages were? Is that the idea?
Well, in this case, they only have to distinguish between was the all zero string encrypted or the other string that we picked.
Right. Okay, great. Thank you.
Yep. Okay, so far for setting the stage. Now our first result shows the following, namely for any of such scheme, any encryption scheme that encrypts classical messages in the quantum messages, there exists a cloning-indistinguishability attack, so one that fits in this scheme, such that actually we have a lower bound on this probability, on this winning probability of 1/2 plus some mu that I'm going to explain over 16. So this mu, it's actually the largest eigenvalue averaged over the keys of the ciphertexts. So I will come back to that statement in a bit, and then I think you will have a better idea what this means. But it basically says that you can't really be too close to 1/2, or if you want to be close to 1/2, this mu actually has to be negligibly small if you want to be negligibly close to 1/2. So as I said, I'll come back to this point. So what is this attack? I kind of want to prove the theorem, or at least I want to show you what this attack is that we come at. And it's somewhat generic because it works in a very general form. And here is kind of the formula for it, but maybe the intuition behind is even more important. Namely, it takes some information in the a cloning attack happens here. Huh? So here is the cloning attack maps whatever comes in on register R to copies in A and B. And what we suggest is to kind of either give R to Bob, this case, or give the contents of R to Alice. And we give some dummy symbol, bottom here, to the other player. But we do that in superposition. So that's kind of defining what this quantum channel does. So bot is just a state that is orthogonal to anything that comes in register R. So it's something that you can always distinguish from whatever output. And you can think of it as like, well, you don't get anything. So in this case, kind of in this branch of the superposition, Alice doesn't get the state, but the whole content of R goes to B. And in here, it's the other way around. And we do that in superposition. That's just a suggestion for a possible cloning operation. So how well does it work? Well, here's a bit of analysis. And we're gonna look at the kind of the simplest example. I also took away actually the example, like the key part. I kind of abstracted away from that because I'm just gonna look at the simple case where X is a random bit, just a single bit. And it's not encryption of it, it's really just the X that is sent along. And now we do that cloning operation with that X. So we either give X to Bob and bottom to Alice, or X to Alice and bottom to Bob. And we do that in superposition. So this is just writing out what the state is if you do that. So the overall joint state, even with X, that should be an R. So the R register is just a random bit because that's picked at random here. So it's either 0 or 1. And then it's the cloning operation run on this R. So either this 0 bit is with Bob or with Alice. And this is just the bra of this projector here. So that's the state. And the question is now, what is the maximal simultaneous guessing probability? So now both of them, both Alice and Bob, given their kind of side information, want to figure out what this bit is. And so they can do local measurements, Px and Qx, run on this cloning operation, run on X. And the question is, how well can they do? So what do you guys think? All you can do? I guess this format is really not made for too much interaction, but are there any suggestions?
Please feel free to write on chat or raise hand or something if anyone wants to speak up. Can I ask a question?
Yes, sure.
So to me, this seems to suggest that maybe the definition is like the superposition, the fact that the superposition attack works suggests that maybe the definition is not the right one, but I don't really I don't know what definitions in this area look like. So,
right.
But still it just like,
yeah, that's maybe an interesting discussion to have. Maybe also Sebastian is here, so he could answer. Maybe we can actually discuss that at the end. So whether this could be an indication, whether a different definition of view. I mean, it's definitely a strong one. So, and the funny thing is here with this attack that indeed this probability is. So let's see, there's some. This just shows up again. So the point is that indeed what we can show, and that's kind of why it's a blue box. The blue are kind of the theorems, green are my definitions. So this guessing probability here is actually 1/2 plus 1/16 plus some constant fraction, even for a single bit. And that's kind of funny because you would think like, I mean, both Alice and Bob have to find this bit. And they're basically either in this branch or in that branch. And in this branch, well, Alice doesn't know anything about the bit. Now she got bottom. So Bob should be able to guess the bit perfectly, but Alice should have no clue. Whereas in the other case, it's the other way around. So both of them succeeding, you would expect that the probability should be 1/2. At least that's what was my intuition. But that's not true. So apparently you can do better than that. So I do see some chat message popping up, but maybe I'll just give one more kind of intuitive explanation for that, and then we can get to Eric's message. So here's a little bit more explicitly what they do. So you can actually do local measurements, and they of this particular form. So they define a state phi, which is kind of 3/4 checking whether it's 0 plus 1/4 square root of it bottom. And then you kind of project onto that state or on the complement of that. And if both Alice and Bob do that and you calculate, well, you'll get this number. So intuitively, they kind of can exploit the coherence in this one getting or the other getting to do better than just not knowing in that case. So intuitively, you would say, well, if they're in this branch of superposition, Alice doesn't know, but that's not quite true because she can actually do a measurement that involves this not knowing. So the fact that there's an additional state there, actually that allows her to do something in addition. So that's kind of my intuition for it, but maybe other people have a different explanation for that. Maybe now, I don't know if it's a good time.
Yeah, I can read out Eric's question. So he asks, this looks like a coherent version of the optimal cloning machine by Werner. Can you comment on the relationship or whether that would work as well?
Okay, I actually don't know. I'm happy to investigate. I don't know that particular case, but it's very well possible. I mean, it wouldn't be a surprise to me if people have kind of observed this before. But yeah, great comment. Something to follow up.
And sounds good. Eric, if you want to follow up, feel free to unmute yourself and speak. Or if not, then maybe you can discuss at the end of the talk.
Sure. Okay. Getting back to this theorem. So now you kind of see where the 16 comes from, and indeed this generic attack. So this fact of like giving the whatever comes in R in superposition to Alice and Bob allows us to do this attack. And as I said, ideally we want this winning probability to be close to 1/2, so 1/2 plus negligible at most. So if you want due to the attack and this to be negligible, well, we at least know now that this mu actually has to be negligible in n. And in fact, because this is the largest eigenvalue of the ciphertext, it means that the ciphertexts have to be pretty mixed. So to make sure that none of the eigenvalues are large, you have to be close to kind of completely mixed state. And so that means that you actually have to make the states big. So they have to be mixed over a large dimension if you want to be able to fulfill this with something negligibly close to 1/2. So that's kind of the our first result here. And that is also historically kind of provided the motivation on what is coming now. Namely, in the second half, I want to talk about this problem of local simultaneous state discrimination. This was our original motivation to study this or to come up with this problem. So what is the problem? The task at hand is the following. We start with a so-called CQQ state. So this is a 3-partite quantum state where the first register is classical. It has some classical probability distribution X. And then you have a set of states, bipartite states A, B, and X just says which of the states you're looking at. So that's kind of the generic form of a CQQ state. And you can see kind of the task works as follows. You first sample this value X according to this distribution Px. And then you send this bipartite state, the one that is determined by this X, to the 2 players, Alice and Bob. And they basically just should figure out what X is. So locally, without any communication with the other person, by just getting their part of this bipartite state, they should do a measurement, and that should tell them what X is. So basically, they just have to, they win if and only if both of them correctly guess X. So that's what we call the local for, they're only allowed local operations, simultaneous because they're not allowed to communicate, and they have to discriminate which of the states row A, B, X was sent to them. And kind of the quantity we're interested in is this optimal success probability of this task, which is basically the supremum over these measurements. So they do the optimal measurement, and that's the success probability. So they get the state, they measure that, and this measures like whenever they are right, basically. Now, of course, we can start adding complications or kind of making it, we do this almost standard thing. If you've seen non-local games before, we can also consider the situation where actually Alice and Bob, they share some resources to start with, maybe quantum resources, for instance. They could share entangled states. And then we can define an analogous quantity, I mean the quantum optimal success probability of this task, simultaneous guessing probability, where we almost have the same formula as before, except that we have some additional shared entanglement here. So this sigma A prime B prime is some additional state that we also optimize over. And now their measurements are over bigger spaces because they can take into account this additional entanglement in addition to the states they have to distinguish and to start with. And a priori, it's really not clear what the relation between these two things should be. That's kind of what we want to investigate here. So let's simplify our lives a little bit by actually just considering classical input states. So that means that simplifies things in the sense of that now these states rho A, B, X are just of that simple form. And basically you have a joint classical probability distribution. So that goes as follows. It basically X, A, and B are all sampled from this joint distribution. These inputs A and B are given to the players. And again, they have to do this measurement and they win if they're right. If they can figure out based on their just classical value A, they can figure out X, and Bob based on his B should be figure out X. Now, of course, actually things simplify a little bit in this case because they don't really have to do a quantum measurement. There's nothing quantum here anymore. So in fact, really, it boils down to maximizing classical functions F and G. So F basically saying what Alice answers given her input A, and G what Bob answers given his input B. And if they both kind of say X, the right thing, well, they win. here is a very simple observation to make, and that is analogous to the world of non-local games, namely that if they have shared classical randomness, then that's not helping them in this task. So even if they kind of, you give them classical randomness in addition, that's not going to help. And the proof is the same as for non-local games. The players, they could simply fix this shared randomness to the one that works best for them. So the success probability would be an average over this randomness. And you can just fix the random string, the shared random string to the one that optimizes their success probability. So in that sense, it's useless to have some extra shared randomness here. That's for the case of classical input states. But of course, now if you give entanglement, well, we get back to the same definition as before. Again, it simplifies slightly, but now there are measurements because the measurements, they can depend on the inputs that the players get, A and B. So, and now they basically measure their shared entanglement and see how well they can do. So clearly this is more powerful, so that value is bigger or equal to that value. But are they the same? Are they different? Yeah, that's what we were wondering. This expression can be simplified slightly to kind of write this as a norm of and kind of get rid of that maximization, but I think it doesn't actually matter for what follows. So let me make an even more concrete example to illustrate these things. So let's say, again, very simple, X is just a random bit, fully random bit. And we basically use binary symmetric channels. For those who know about information theory, or like explicitly, you can say A is just kind of some noise added to X. So A is a noisy version of X, and B is an independent noisy version of X. And the noise is Y and Z are just kind of, again, binary random variables that are 0 with probability alpha and 1 with probability 1 minus alpha. So it tells whether the bit is flipped or not. So you can think of like two independent binary symmetric channels applied to X to get A and B. So that's describing the joint distribution. And the task is still the same. So kind of do the best measurement to figure out what X is. Again, here you don't really need to measure because there's nothing quantum here. But if you plot, kind of figure out what the optimal success probability is in this task, you get something like that. So this is actually not quite a straight line. It's a little bit curved, and it's not so hard to figure out what that is. But you see this kind of interesting two regime behavior. And it's intuitively pretty clear what happens. Because if you have low noise, so imagine like no noise, for instance, well, then clearly the best thing to figure out X is just output, Alice outputs A and Bob outputs B. So if you have small noise, then that's kind of what they're doing. And the success probability is just that no error occurred. So that kind of both Y and Z are 0, so nothing was flipped. And the probability, because they're independent, is just 1 minus alpha squared. So this happens up to this point. And at that point, we kind of, instead of going further down this curve, there's another best thing to do. We kind of get into another regime where there is a lot of noise, just from this critical threshold on. And now it becomes better to just coordinate your guesses. So even though you might be wrong, the best thing now becomes just outputting 0 or outputting 1, because because X was picked at random, uniformly at random, well, your success probability of guessing right is going to be 1/2. But at least you're always saying the same thing. So you're never making this error that you're not coordinated. Because remember, you can only win if both the players are right in this particular task. So you kind of get this two regime behavior. And something similar has been observed by Eric here on this talk and Laura Manchinska. But then in the quantum case, so they actually also studied this problem, and they also actually long before us already looked at this setting of local simultaneous state discrimination. And we weren't aware of that. And they already had some example analyzed where they also see this kind of two regime behavior when trying to distinguishing quantum states. So this here shows that you already kind of get that if you only look at classical input states. So that's a first little example. and now basically we're ready to summarize our contributions, and then depending on how much time I have left, I can go into some more details about those. So, well, one of our contributions is to define the problem, kind of very naturally, just like you have only local operations and you have to, both of them have to be successful. Already for completely classical case, you get this two regime behavior. And our first result actually shows that there is an example, again, purely classical. Basically, all our examples are just purely classicals of a joint distribution, namely this one here, where these three values are all different. And so we can actually see a difference between the case where you are given quantum classical resources, so basically no shared quantum state to do this task, versus you have some entanglement, versus you have something even more powerful, namely non-signaling boxes. So I really haven't really formally defined what that is, but for those who have seen non-local games before, they know that you can define a kind of more advanced value as well. And at least for classical input states, it's kind of clear how to define those, but I'm more glossing over this. But indeed, in this example, we can actually show that all these three values are different. And I personally didn't really know what to think beforehand, but yeah, I find it somewhat surprising that they actually are different, that you can have examples where it makes a difference whether you get entanglement. Well, afterwards okay, it's maybe less surprising once you've seen the result, but before we really had no idea how these values would behave. And then there's two more results that I think I will come back to because I think there's enough time to talk a little bit about the first. So here's this example that I just outlined, and basically it's a uniform distribution over 5 possible input triples, so it's just a joint distribution. And notice that A and B are just bits, whereas X is actually a trait, so it has 3 possible values. And yeah, the classical value of this game we can compute exactly is 2 or 5, so 0.4. The quantum value we could also compute exactly, which is 16 plus square root of 13 over 45. And the non-signaling value is a half. So you see, like, all of these 3 values are distinct. Now, how did we do this? Actually, that was quite a journey, and I definitely won't go into details. But there's some kind of interesting characterization lemma we came up with that at least characterizes the classical value. This one is still easy to state. So there are some maximizations you have to take about S and T. So here they are just bits, and it's a maximization of these 3 things. And there it's pretty easy to just check that with this input distribution, we basically have that the probability that the X is 0 or 1, that's 2/5, that's 2 of the rows. And that one is 1/5. And for all other values, you also have 1/5. So clearly, once you assume or you accept that this is a proper characterization of the classical winning success probability in this task, then it's easy to kind of conclude that this classical value is 2/5. And a similar thing can be done for the non-signaling value. There it's a bit more complicated. So we have a similar lemma that kind of gives a characterization for this case. And then we basically give explicit strategies that work for this example. And that gives that the non-signaling value is 1/2. And then definitely most of the work was to figure out the quantum value. And that was Maris, who is an expert in doing these things, doing a bit of numerics. But yeah, this gives an idea. So we can just prove that it's exactly this value here for this example. And actually it can be achieved with an explicit state and an explicit measurement on just 1 qubit each. So they share an entangled state where both Alice and Pop have just 1 qubit, but it's entangled, and they give an explicit measurement that achieves that. But then to show that it's optimal, we first assume that their local dimension is 2, so they have a qubit, and they're using projective measurements. And then you can parameterize the problem, and then if you show that some matrix omega that is given here is the norm of it is smaller than this t star value, and that should hold for any AB between 0 and 1. And that reduces to kind of some characteristic polynomial, and Maris indeed actually managed to find a sum of squares representation of this polynomial. So that was kind of a tour de force, but we do have an analytic proof now that actually this is the optimal value. And then the general strategy, it reduces to the kind of special case above by using Jordan's lemma. So those who have seen this before, this might, at least the ingredients might look familiar, but this is quite a bit of actual numerics and playing around, and also being a bit lucky to actually find a sum of squares representation of this to get an analytic proof. All right, so that's kind of our main result, I would say. Then the other two are kind of smaller things that maybe I can touch upon. There's enough time. So the next one is actually stating that this is not always the
Christian,
case. Yeah.
Can I interrupt you? I think
Yes.
there's a question by
Yes.
Eric.
Yes.
For clarification, is this optimal only for local dimension d equals 2, or?
For this example, it is, we know that this is the right value. So then it depends what this is, what you meant by this.
So,
I don't know if you want to clarify now, or maybe we can also discuss it afterwards.
Yeah, that sounds good.
Okay, that's good. So in a sense, there is some optimality in it, namely given by this next theorem. The fact that these values are different, this cannot occur if X, A, and B are all binary. So A and B are binary in our example, but X is not. And actually that's necessary. So this is kind of showing that this is maybe the smallest example, one of type of smallest example you can find where X is a non-binary value in order to have this difference between the two. Because if all three values are binary, then we can actually show that these three values coincide. Then again, this is using, the proof is using kind of this characterization that I showed on the last slide, so in spirit. And then lastly, we actually show that for three parties, this computing this, the classical success probability is actually NP hard. And maybe I can spend the rest of my time to kind of explain that. I think this one is maybe a bit too complicated. That's another thing we kind of show that in this example, it doesn't really behave. I mean, it has a bit of a parallel repetition flavor. So if you take independent copies of the problem, then these success probabilities don't kind of behave in a product way. But you can do better if you get independent copies. And again, with this example we had previously and this result together, we can actually show this pretty easily. So there's some interesting stuff going on here. So finally, the multipartite local state discrimination problem. Well, multipartite is easy because you could just simply have more parties. You know, like if you start with a 3 or 4 partite state, then obviously you can sample this distribution and just give A, B, and C to like 3 players, and they all have to guess what X was, and they only win if all of them are right. So that part is pretty clear. And now for the other parts, kind of to show the NP hardness, we will reduce it to some classic NP hard problem. And for that, we need hypergraphs and matchings. And basically all the pictures here are taken from this Wikipedia page. So you need to, I guess you're all familiar with graphs, I assume, like they have vertices and edges. And hypergraphs are generalization of it. So hypergraph, you have hyper edges. So those are in this edge set E. And those are simply non-empty subsets of the vertex set. So instead of just having edges that connect 2 vertices, you can have subset of vertices. So in this example, like we have like E3 is a hyper edge containing the vertex V5, V6, and V3. So so this is a picture of a hypergraph. And now you need to know what a matching is. So normally a matching are just, well, mutually disjoint edges, so edges that don't share a vertex. And that's the same here. So it's a subset of all edges that are mutually disjoint. that's the generalization to hyperspace. For instance, an example, so E1 and E4 would be a matching. So E1 has like this yellow thing, and E4 is that they are disjoint. So that would be a matching in this graph. Or E3 and E4, and so E4 is disjoint to everything. So that would be a matching. But E1 and E3 is not a matching because they overlap in vertex V3. So they have to be disjoint. And now the challenge is to kind of find the maximum cardinality of a matching. So finding matching is itself is easy, but you want to find the biggest matching. So you want to kind of find the biggest subset of edges that are mutually disjoint. And it turns out that that is hard, even in some particular case. So what we're gonna do is we're gonna restrict ourselves to 3-partite hypergraphs. So those have a special form, and here's a picture. So each hyper edge, so those are these gray thingies here, they contains exactly one vertex from each part. So here we have 3 parts. So the red vertices, the blue ones, and the green ones, and the hyper edges they're connecting exactly one vertex from each part with each other. So here's a bunch of hyper edges, and the problem now is to find matchings in such 3-partite hypergraphs. So find subsets of these edges and find the maximal subset. So this would be a matching because they don't intersect, but this would be the maximal matching. So here you have kind of out of these 4 hyper edges, we can take these 3 and none of them overlap. So here this new of this hypergraph would be 3 because we can find 3 hyper edges that don't overlap. And then the result, and actually, so that goes all the way back to CARP, computing this maximum cardinality even in 3-partite hypergraphs is NP-complete. So that means if we want to show, one way to show that something is NP-hard is to kind of embed this problem in it. And that's what we do. So here is this 3-partite hypergraph. What we're gonna do, how do we define our joint distribution? Well, we're gonna do it as follows. Just take such a graph, a 3-partite hypergraph, basically pick an hyperedge at random. So out of these 4, you just pick one of them at random. And then that by definition of 3-partness of this graph, you give these vertex from that hypergraph to the players, and they have to figure out what the hyper edge is that the referee picked to start with. So here in this case, you would I'll give for instance this, and that vertex to the players, and then they have to come up with that hypergraph. And now, so that's kind of how this joint distribution is defined. Now I think it's not that hard to see that the best classical strategy actually will be exactly this matching, this maximum matching of this hypergraph divided by the number of edges. And somehow the intuition is that the best way to answer is kind of to fix such a maximal matching. If you have that as your strategy will be whenever, for every player, if you agree on this, on the maximal matching, well then whenever you get this vertex, well you're gonna say that edge, so this hyper edge. So that's the intuition. That's indeed what we can show, that the best strategy is kind of finding the best strategy in this simultaneous local state discrimination game is to kind of agree on a matching. And yeah, well, finding those is NP-hard. So computing this value is also NP-hard, at least for 3-partite. So here, notice we kind of had to extend by 1 player, because for 2, it's actually not true. So if you only have 2 players, then this finding a maximal matching is, there's efficient algorithms for that. So in this example, this won't work. And we can also connect this a little bit with the non-signaling value, but I think we'll not go into the details now. So actually, I think I reached the end of my talk. So a quick summary of what I've been talking about. So on the one hand, we had some contribution to the area of unclonable encryption. In particular, we showed a generic cloning attack namely this idea of kind of distributing in superposition the information to one guy, the other guy, and then they can do some clever measurements that gives them some additional information. And then we defined this problem of local simultaneous state discrimination, and we kind of showed some first result, in particular an example where these values are different, and some cases where they actually have to be the same, and some NP-hard as a result of computing those. But of course, there's many open questions associated with this. I did not have time to make a whole list, but I think this is just the beginning of further investigations into that. And I think this problem here is kind of cute enough, both for the kind of quantum guys, because it's related to state discrimination, but also for the crypto people to kind of tie into the whole area of unclonable cryptography. So that brings me to the end of my talk. Thank you very much for listening, and I'm happy to take more questions now.
Thank you, Christian.
Thank you.
I'll get started with the question, and anyone else that has questions at this point, just feel free to unmute yourself and speak, or type in chat if you don't have a microphone, and I can relay your questions. Yeah, to get started, I was wondering if there are connections also. I know you unclonable crypto tasks like copy protection, etc. And while you demonstrated this connection to unclonable encryption and the impossibility thereof, what are the connections with other unclonable tasks?
Yeah, who knows? I think that's kind of, yeah, we were motivated with by the connection with unclonable encryption, but I'm pretty sure there's more. There's more to investigate. Maybe even
but
with
like, are there?
Yeah.
Sorry, I was just saying, are there simple translations of these results from unclonable encryption to other things, other unclonable things like unclonable, like secure software leasing or copy protection, where you could just lift some of your results and say that would imply unclonable encryption with these parameters, and so that's impossible.
I'm not aware of it directly, but I would also not I would also not exclude it. So I think somehow the area is still kind of new enough that maybe even the totally simple, well, maybe the totally simple things people have seen yet, but yeah, I somehow also, like from Anne Broadbent's tutorial talk, I think it becomes clear that there's still stuff to investigate. So it's yeah, is there kind of a fundamental resource of unclonability where these things can all be based on, something like that? That would be exciting. I don't know. I somehow I have the feeling that the dust has not settled yet. So it's not like that we see through and we say, oh yeah, it's like that. So I think the connections are still to be explored.
Thank you. Yeah, I'll leave the ground open to other questions. Also, Hannah, would it be okay to stop streaming live?